Okay, so what we're going to do actually, it has a name. It's called dimensional analysis. Uh, and analysis. And so what dimensional analysis looks at is it looks at how units relate to one another. Okay. So just before we start, we just need a little tiny background on the metric system, um, and why it is the preferred, obviously modern, I guess, system for measurement used pretty much everywhere in the world, except for a couple of places. Um, so background on the metric system. So before the metric system, different parts of the world had their own kind of measurement systems, and there's been a lot of historical measurement systems, um, going back to when people first started to use measurement. Why do you think measurement began in the first place, or how do you think measurement came to be? Why do people measure? Okay, what, like, where is it needed in a human society? Like, do you think that like our ancient like animals don't use measurement, right? Like, why is it that humans need to have measurement? Yeah, right, right, right. Sure. So we'll say commerce or probably farming, right? Trade, etc. Without a system of measurement, it's pretty hard to have an economy of any type, right? And when you have a human society, if different people are doing different jobs, right? If it's one sector of society's job to produce food, and another sector of society's job to say, build housing, you have to have a way where people can trade jobs with each other essentially, and that works out to be to require measurement, right? Like if you say, I will give you, so much livestock if you build me a house, right? You have to have a way of like kind of organizing that, and eventually that comes down to money. Or if you're like, trying to figure out how much land you bought from someone, right? You need to be able to measure that out, and there needs to be a standardized way where you and I in our society can discuss things and understand each other. If we want to build something and I design it and you're supposed to build it, we have to have an agreed upon way to measure things out, right? Here's a really maybe simple example. Like, let's say you want to buy um, fabric or something, okay? Let's imagine we're in an ancient marketplace, okay? And so the merchant selling the fabric has a big giant roll of fabric sitting there, okay? And you come up and say, I'd like to buy, some amount of fabric, and you got to tell him how much it's going to be. So for um, for this example, let's say we're using feet, okay? And probably, although I'm not exactly sure, but feet probably came from someone literally pulling out a length of this and probably, walking along it with their feet and, literally measuring it out, okay? And that's probably okay, except when you get to things that are of great value, right? Maybe this merchant has gigantic feet, okay? And the customer says, well, I want this measured out in my like 4-year-old kid's feet because they're very tiny, right? So, um, or wait, maybe that's the other way around. The merchant brings out his 4-year-old kid and says, here's your 3 feet of fabric, and it's like a really tiny amount, versus the customer who has gigantic feet. That's probably a better way of saying that, right? So without standardization, um, you run into these kind of problems. So one thing that's important to have for measurement systems is they have to be standardized, and that just means that everybody is using the same value for a foot. So likely what would have happened is you would have taken maybe the monarch or the king or something like that, and probably measured out his foot and said, well, now all feet will be measured in the king's feet. Okay, so now we have rulers that are, measured out in standard feet, and everybody in the kingdom or wherever we're talking about will use that value. Okay, what is the actual connection to nature of this? Nothing. It's the guy's feet who happened to be in charge when feet were standardized. Okay, um, if you look at the imperial system of measurement, it has feet. It also has inches, and usually if you take an inch ruler and you lay your thumb across it sideways, you'll find that the thumb and the inch are pretty darn close together, as are the foot and your foot. My foot actually just happens to be almost exactly the size of a true foot. Someone's might be bigger, someone's might be smaller, just so happens. And my thumb happens to be roughly the same size as an inch, and probably yours will be too. Some other ones are hands. People used to use hands, and still I think horses are measured in hands. There's yards. I believe a yard is the size of a normal stride, essentially. So you would basically, yeah. So 3 steps is how far you would go when you took a step. There's the league, if you want to start looking into it, and that's how far a Roman legion could march in a day, and so on. Now the problem, the problem of standardization, well, that was dealt with by standardizing all these measurements to a certain size, but there's a downside, right? As societies evolve and move along, well, there's a few downsides. One downside of this is that there's 12 inches in a foot, there's 3 feet in a yard. I don't know how many yards there are in a league, I'm not really sure. There's like 2,400 and something feet in a mile, or is it 20,000? Okay, hang on, we'll double check. 60 yards, okay, in a mile, and then 3 times that in terms of feet, right, and so on. So you get all these kind of oddball, unit conversions that are kind of difficult to deal with. Our lumber still comes in this system, and so most people, like at least in North America anyway, build in this system. But I think that you'll find that when you kind of start to immerse yourself in the metric system, you'll find that it makes life a heck of a lot easier. Okay, so problem number 1 is conversions are odd, like very weird conversions here. Conversions are weird. Okay, and if you start to delve into this, there's actually a whole bunch more measurements in here that you don't often see. The smallest measurement, it's actually not the inch, it's the barley corn, which is the size of a barley corn. There's chains and Gunther's chains and all sorts of different odd measurements that come out of this system. It is standardized, but it's also odd, and it doesn't really have. The other problem is it doesn't have a connection to nature. So there's no real connection to nature. Once the person whose original foot measured the size of a foot dies, how can you replace the foot should all of the rulers in the world suddenly disappear, right? And no one would really know how big a foot was. We'd have to reinvent the foot, and then all measurements subsequent to that, right, would be out. So if I walk around my house with a measuring tape, it's kind of interesting. You start to measure things around your house, like the width of your computer monitor, or like how the size of your desktop, or your TV from side to side. You can kind of start to figure out whether these things were measured in metric or in Imperial, by the sizes of things, because everything kind of comes out to some even number in either one system or the other. But the problem is, right, that if we were to lose all our tape measures and all our rulers in the world, how would we know what a foot originally was, right? Or anything measured in feet, right? Was this a foot? Was that a foot? How big was a foot, right? So these are 2 sorts of problems. Conversions are an issue, and size is an issue, right? So to combat that, around the time of the French Revolution, actually this concept was actually older than the French Revolution, but after the French Revolution, it was put into place in all the lands kind of that were eventually conquered by Napoleon. He brought in the metric system, and it has as its base the meter. Notice the spelling, it's METRE, which is a thing. To meter is to measure something like a parking meter, right? A parking meter measures like, I guess, time, right? The meter is a thing, okay? So the meter is the base of the metric system. And I'm sure you already know this. The name metric comes from the term meter. So what's a meter? Why is a meter better than a foot or an inch or a yard or whatever? It's kind of the size of a yard, but not exactly right. Not exactly the same. Any idea where the meter originally came from, or why it's something to make note of? Well, yeah, right. So it's SI, right? System International is essentially the other name for the metric system. It's what's used in the scientific community, and most of the world uses this as their day-to-day measurement. In North America, at least in Canada, we have a hybrid because we're officially on the metric system. So we buy things like gasoline and so on in SI units, but because we were only on the metric system, or have been on the metric system only for about, I think, like 40 or so years, 45 years. There's lots of people around who grew up before the metric system, so we often talk about our weight in pounds and our height in feet and inches, and our roads are measured out in miles, even though our speed limits are in kilometers per hour. So we're in a kind of a strange hybrid between completely metric and the old style system. But anyway, okay, so SI is just another kind of name for the metric system. So let's just think of what two problems we said there were with the older system. One, sizes are arbitrary, right? Arbitrary just means, I mean, it is what it is because of kind of almost like happenstance, right? The foot is the size of a foot because of some guy's original foot was the size of a foot. It was the size that it is. The inch is roughly the size of a thumb, and roughly, if you lay your thumb sideways across your foot, you will get about 12 inches in a foot, and so on. And this is kind of where all that comes from. Sizes are arbitrary, and two, there's not really a connection to nature. So there's nothing in the natural world that you could rebuild something like a foot from, right? Once the foot disappears, no one will ever know what the size of a foot was again, okay? Think of a measurement like, say, a historical measurement is a cubit, right? Now, we probably still know what a cubit is in more modern measurements, but roughly what a cubit was the distance from your elbow to the tip of your finger, okay? So if you go back to like biblical measurements, people were measuring things like the ark in cubits. We all kind of probably know that story. But it was an actual day-to-day measurement. And I believe it's Egyptian. I'm not 100% sure, but I think it's Egyptian. I think the Egyptians, would have used that as the base of their kind of their measuring system, and they would have had all, I guess, numbers based off of that. If you go to Asia, they have their own, like the Japanese had their own kind of measuring system, and so on, right? So all the world had its own localized measuring systems based on whatever happened to be there, right? And all of them, none of them that I'm aware of anyway, had any connection whatsoever to nature. So the metric system tries to fix this. And number three, conversions were a problem, right? There's a problem with conversions in the other system. There's no, way to convert easily between values unless you know what the conversion factor is. So how do you fix that? Well, let's start with figuring out a size that isn't arbitrary. So one way to do this is use something in the natural world to to base your system on, right? So what they did was they proposed that if this represents the Earth, okay, and that's the equator, you survey the Earth, you should be able to measure the distance from the equator to the North Pole, okay? And if you divide this into 1/10,000,000th, what do you think you get? 1 meter. So 1 meter comes from the size of the Earth itself, okay? By the way, this was on a line measured through Paris, okay, and that's meant to represent the Eiffel Tower, even though this was done before the Eiffel Tower was invented. So the French surveyed the size of the Earth, okay, and they figured out exactly how far it was from the equator to the North Pole, and they took that line and they divided it up into 10 million. Now you might ask, why 10 million? Why not 100 million? Or why not 1 million? Okay. What's special about the size of a meter? Grab a meter stick or look over at a meter stick or think about a meter stick. Why 1/10 millionth? Why not 1/1 millionth? Or why not 100 millionth? What can we say about a meter stick that's useful? Yeah. Well, can't say that because centimeters were defined after the meter. Is the meter a good size for an everyday life measure? Yes, it is. Someone yelled no, but based on the fact that you're kind of stuck if you want to keep everything on the 10 system, and we'll talk about that in a minute. You're either going to go with one less zero here, and now the meter is actually a kilometer, and that's your base. Well, that's too big to be useful, right? A kilometer, if you're trying to measure, something like your height, you don't want to do it in terms of kilometers. You could, but you're now doing a tiny fraction of a kilometer, right? And if you go another one, well, now the base unit is going to be the millimeter. Is that right? Sorry, 1/10 of a meter, a decimeter. I guess at the time that was probably deemed to be too short to be of general use, right? It would be a little bit smaller than, say, a foot, right? So just this line through Paris thing. There's nothing, significant about a line from the equator to the North Pole that runs through Paris. It's just that the French were doing this, and it's a symbolic gesture, right? So 1/10 millionth was decided upon because, a base unit that's 10 times bigger probably is too big. And I said a kilometer, but it shouldn't be a kilometer. It should have just been 10 meters. 10 meters is too big as an everyday unit, and 10 times smaller is too small. So they went with 1/10 millionth rather than 1/1 millionth or 1/100 millionth. I wasn't there, but I assume that's the thinking behind that. So that's where the meter comes from. The beauty of that now is that if you were ever to lose all the meter sticks in the world, you could resurvey the Earth and you could rebuild the meter, right? You could get it back if it were ever lost. It's based on a physical property in nature. Nowadays, they've much more precisely defined the meter, and it's based on essentially the distance that a certain frequency of light travels in a certain amount of time. Okay, so it's very, very precisely defined nowadays. I mean, wavelengths of light are extremely short, so that much more precisely defined than 1/10 millionth of the distance between you. By the way, the Earth is not a perfect sphere, so this value is actually not exactly 1/10 millionth. The size they came up with is not exactly right, but that doesn't actually matter at this point. So what did they do? Once they had this, they created a prototype meter. Okay, so they created a prototype meter out of a type of metal that does not corrode. I believe it's some alloy of platinum. Okay, and they made this meter, and this is the prototype meter. Okay, and it's very valuable. It's kept, I think, even to this day. Although I'm not sure, because I'm not sure about what happens with this wavelength business. But it was kept in Paris under lock and key and guard and so on. And what happens is they make copies of this and they send them out to other parts of the world that are under the metric system, and then all of their official weights and measures are based off of this. So like if you say want to manufacture a meter, you can probably go and you can probably get access to some copy of this original prototype meter, and that's what you make your meter stick based off of. I don't know what the laws are around measurement, but you can imagine there would be major problems if you started selling measurement tools that were slightly off, that you're just like, I think this is a meter, right? And you started to like, say build bridges with, slightly the wrong values, or say like, gas up airplanes with your own version of the kilogram, right? You might have problems. So moving along from there, how do we get an entire measurement system from this one single value? Because it's called the metric system. So let's imagine we have this meter here, right? Here's our prototype meter. Oh, I wish I could draw a straight line. Okay. Well, we can start dividing this thing up. If we cut it into 10 little individual parts, right? So there's 10 little individual parts. Those are called decimeters. So 1/10 of a meter is a decimeter. 1/10 of a decimeter ends up being, what do you think? A centimeter, right? So there would be 100 of these in an entire meter. And if we cut a centimeter into 10, what do we get? We get a millimeter, right? Millimeter. So a millimeter is there's 1,000 of those in a meter, okay? If you go smaller than that, you would get you'd get 1/10 of a millimeter, 100th of a millimeter, 1,000th of a millimeter, and then you would get to the next thing where there is 1 times 10 to the 6 of these, or a million. So 1,000 and then a million, and that is a micrometer. Micrometer. And micro has this funny symbol that looks like a U. And if you go even smaller, okay, so this is 1 billionth, right? So 1/10, 1/100th, 1/1000th. Then there's a gap. It doesn't get prefixes, so you just would go 1/10 of a millimeter, 100th of a millimeter, 1,000th of a millimeter. 1,000th of a millimeter is now a millionth of a meter, because you're 1,000th of 1,000. 1,000th of 1,000. So you're now into a millionth. 1/1,000,000th. That gets micrometer. Then you get 1/10 of a micrometer, 100th of a micrometer, and then you get to 1,000th of a micrometer. You're now into the billionths. Anyone know what this is? What kind of meter is there a billion of them in a meter? A billiometer? No. Think about iPod has something called this. A nanometer. Very good. Nanometer. So iPod Nano. Nano means really small. And if you go beyond that, anybody know what this is? A trillionth of a meter? I'm not sure. I'll have to double check on this. I think it's a picometer. Let me double check on that. I think there is stuff smaller than a picometer, but I mean, for all intents and purposes, if you need to measure accurately to a trillionth of a meter, well, I just think you're probably working on stuff that's well beyond, like we would never have to go that low, right? And then you can go the opposite way, and you'll notice, right, that all of these are essentially orders of magnitudes. They're all based on multiples of 10. No 12s, no 3s, no, what was the other one? 1760s, just 10s. 10s everywhere. So it's rebuildable, and it's based on 10s. It's brilliant. No fractions either, right? No 3/16 plus, 5/8 or something like that. You don't have to do that, right? You just add and subtract centimeters, and away you go. Life's good. Also, called out on spelling meter wrong. All these meters should be REs. Sorry. My mistake. I think you can get away with either way, technically, but it should be RE for all of these, okay? So let's just go up the other way, right? So if we have 10 meters, does anyone know what that's called? Anyone know? Deca meter. Good. Deca meter is 10 times bigger than a meter, right? It's 10 times bigger than a meter. If we want to go bigger than that, we go 100 times bigger than a meter. Anyone know what that is? Hectometer. Not often used, but, there we go. And then 1,000 times. Kilometer. Excellent. Okay, then we would go, 10 kilometers, 100 kilometers, and then 1,000 kilometers or 1,000,000 meters. Anyone know? Mega. Megameter. Milla? No, not milla. Mega. That's 1,000,000 times a meter. 1,000,000 meters. And then beyond that, what's bigger than a mega? Giga. Giga. 1 times 10 to the 9, anything bigger than that? Tera. Tera. 1 times 10 to the 12, that's a trillion, that's a tera. And yes, there are larger ones, but they get strange, like yoctometers and zotometers and so on. Larger than what we would need on a day-to-day basis. Okay, So that's it. This is metric prefixes, and this is the relationships between metric values. So if someone says you have 10 megameters, you have 10 million meters. Someone says you have 500 kilometers, you have 500,000 meters, and so on. And, you know, times that by 100 to get the number in centimeters. Times that by another 10 to get that in millimeters, and so on. The conversions are very, very straightforward and easy. Okay. So now, we don't just have length in the metric system. What else do we have? We have weight. So weight. So what's the basis for weight in the metric system? Well, that's if you were to take a cube, 1 meter on a side, and you were to fill that with water. So this is 1 cubic meter, right? 1 meter by 1 meter by, which side have I not done? 1 meter. And you take a cube of water, and you put the water at 4 degrees Celsius. Why 4 degrees Celsius? What's special about 4 degrees Celsius? It is when water is at its densest. Yeah, I think so. Beyond 4 degrees, if you get colder, water will start to freeze. It'll start to crystallize. It'll actually become less dense, right? If you go warmer than that, well, it's liquid water, but again, it becomes less dense. So they chose 4 degrees Celsius because it's when water is at its densest. Ice is interesting in that it is a solid that is less dense than the liquid, and that's why ice floats. The reason why is because it forms crystals with like gaps in the middle, which allow it to float. Okay, so anyways, water at its densest. Now, if you fill this with water at 4 degrees, I'll give you one guess as to how much you think this weighs. A kilogram? Are you sure about that? A gram? Are you sure about that? Please don't talk about pounds. It weighs a ton. 1 metric ton. Okay? So in other words, if you take 1/1000th of this thing, you get 1 kilogram. Okay? So in other words, the kilogram is defined as the mass of 1/1000th of 1 cubic meter of water at 4 degrees Celsius. Isn't that interesting? So we get a kilogram back from water, which is all over the earth, right? It's pretty ubiquitous. There's water everywhere. And it's pure water, by the way, not salt water, pure water. And you define the kilogram based on this. Now, there's a little bit of a problem with this, okay? The problem is how much this weighs depends a little bit on gravity, right? How hard is gravity pulling down on this object when we put it on our scale? And gravity is different depending where you are on the globe. It's not uniform. So it turns out that this maybe isn't the best way to find a kilogram. And if you search around the internet, you'll find that there's efforts underway to redefine the size of a kilogram. But this was the original method that they did this by. So what did they do? Well, they machined themselves a 1 kilogram, I believe it's called like the master kilogram or something cool like that. Yes, it is. Oh, no, you know what it's called? It's called Le Grand K. No, it is. The Big K. It's the original. All other kilograms are based off of this guy. There's a good Veritasium video. Do you know this guy? He does like physics videos. Anyway, he talks about this. Something interesting that he notes is that there's copies of the Master K, the Grand K made, and they were done, I don't know, like say around 1900 and sent to all parts of the world, and then they brought them back like 50 or 100 years later, and they put them all side by side, and they all weighed slightly different than each other. So there's a little bit of a problem with the kilogram, right? It's based on the amount of water, the weight of water at a certain point, and then it's based on this. So this seems to change with time, even though it's made out of an alloy that's not supposed to corrode or change at all. Okay, so what's the problem? Who knows? Maybe some nuclear decay. We're not really sure. All right. Yeah. So there we go. So there's mass and length in the metric system. What's the other main thing that we need to measure? Height could be measured in terms of meters, right? Time. Okay. Time's a whole nother problem. Okay. we talked a while ago about the 360 and how that works into time and how it's got to do with circles and so on, and Earth's passage around the sun. The base unit is the second, though. 1 second. When you go below seconds, it goes into the decimal system, right? There's tenths of seconds, hundreds, thousands, and so on. So beyond and below a second, it becomes metric. Okay. So the second is the basic amount of time in metric. Nowadays, that's gone by the time for a certain amount of vibrations of a cesium atom, a special kind of cesium atom. So it's very, very accurate. Okay. So that's where the metric system comes from. That's why it's better, and that's why it's sort of weird that we haven't, as an entire, planet of people, switched over to it. Okay. Now, quickly, let's talk about some conversions. Okay. How would we convert in the metric system? Well, let's say convert 10 centimeters into meters. So sorry, that's not right. I'm going to go with kilometers. Okay, so in other words, 10 centimeters equals question mark of a kilometer. So what fraction of a kilometer is 10 centimeters? How are we going to go about doing that? Can anyone do that off the top of their head? 0.01, you think? Yeah. Uh-huh. Yeah, but there's 1,000 meters in a kilometer. Right. So yeah. So what we'll do is we can probably do this in our head with a little bit of thinking, but we can also do a little bit of a method here. Okay. So this method is going to be that dimensional analysis that we talked about before. So what we'll do is we'll say, so 10 centimeters. Well, we know that there's 100 centimeters in a meter, right? So we keep to things that we know. So if we want 10 centimeters in terms of meters, we simply divide it by 100, right? Or we multiply it by the fraction that tells us the relationship between meters and centimeters, right? So what we'll do is we'll get 10 times 1/100th is basically like taking this number and dividing it by 100. So, 10 centimeters equals 0.1 meters, right? I think most people could probably do that in their head. And then the next step is, of course, taking that and doing whatever conversion factor we need to do to get this in terms of kilometers, right? So we know that there's 1,000 meters in 1 kilometer. Now, if you look, if I have centimeters multiplied through on the top, the units here, right, I'm multiplying by centimeters and then dividing by centimeters, so that unit's going to cross out. I'm going to be left with the unit I want. And the same thing's true here. So this is a way that you can sort of check what you're doing. So we need to say, okay, basically whatever we have in meters, that value will be 1,000 times smaller if I do it in terms of kilometers. So divide this by 1,000. Essentially, we're going to move this over 1, 2, 3 spaces. So 0.00. Is that right? Right. Sorry. There. We'll squeeze it in. Okay. So 10 centimeters is 0.0001 kilometers. Okay. So there we go. Does that make sense? Should we illustrate something interesting with the Imperial system? How many miles is 10 inches? You got this? So what conversions do we need to have? We need to have first we need to know the feet in a mile. How many feet are there in a mile? And then we know that there's 12 inches in a foot. Can someone find the number of feet in a mile for me really quick on their device? 5280? Okay, perfect. So we go 10 inches. So we'd have to say, okay, so for every 12 inches, we get 1 foot. So in other words, we have 10/12 of a foot, right? And then the next step is we would say there's 5280 feet in 1 mile. So then we'd have to divide it by 5280. So divide 10 by 12 and then by 5280, and what would we get? What do you got? Yeah. 1.57 times 10 to the negative 4 miles. It can be done, but you have to know that, and you have to know that. And man, this is an easy number to forget. Whereas 10, 100, 1,000, boom, done. Right? Question at the back. (1.57 times 10 to the negative 4 miles? Yeah. So what does the negative 4 mean? It means that this is actually moved over 4 spaces, right? So 0.12317 miles. Why didn't I just write it like this? Yeah, and like what if I said something even smaller than that, like a fraction of an inch? Now what if I want 3/4 of an inch in miles? Oh man, now what, right? So now you got to start with 3/4 up here and go from there. Okay, so if that doesn't sell you on the metric system, I can't help you. Okay,